So why are we doing this? The big idea is that let's pretend for a second that I have a differential equation that can be written in the following form, that I could write it as I have some function times dx plus some function times dy, and that equals 0. Okay, let's pretend that our differential equation is in this form. And for any of you who are wondering, what kind of differential equation could be written in this form, let's just pretend, just give you a very quick example here, that we have dy dx is equal to something like negative 2xy squared plus 1 over 2x squared y. And hopefully it doesn't take too much effort to see that I could rearrange this to be 2x squared y dy is equal to, let's see, we have, that minus sign is supposed to be in the front. I'll fix it in a second. So we have negative 2xy squared plus 1 dx, and then, this minus sign is supposed to be parentheses. And then I can add to the other side, and I end up getting some function, right? I end up getting 2xy squared plus 1 dx plus 2x squared y dy is equal to 0. So I can separate a first order differential equation in this form, where this is what I'm going to call my m function, and this is what I'm going to call my n function. Now, what is the point of this whole thing? Why did I go about reminding you about this thing called the total differential? The idea here is that if, the biggest if of all the ifs that exist, if it turns out that this function right here, or in this case, this one over here, if it turns out that that function there is the partial derivative of some big parent 3D function, and it turns out that this function here, this one here, is the partial derivative with respect to y of that same function, right? So the biggest if in all the worlds. Then what this means is that the left side of this differential equation could just be written as dz. And then the right side we just have equals 0. So you're like, okay, so what? Well, this first equation, this one looks pretty nasty to solve, but this second equation is equivalent, and solving this is like a piece of cake. You can just integrate both sides, and if we integrate both sides, what are we going to get? Well, the antiderivative, hopefully, of dz is just going to be z, or what I'm going to call my f of xy function, this parent function, and the antiderivative of constant, that's just, last time I checked, that's just going to be some, not antiderivative of constant, the antiderivative of 0 is some constant c. And so this ends up being the solution to this differential equation. Okay, whatever this mystery parent function is, right? We don't know what it is yet, but that's the idea. The idea is that if this differential equation, when we split it up, if I can verify that this chunk of it and this chunk of it are both kind of like descended from some big parent function, it turns out that parent function plays a huge role in solving this differential equation, and that the solution we get looks something like this. So, for example, maybe it's not in this case, and we're going to solve it, but maybe the solution function we get is x squared y is equal to 6. Or in other words, that would tell us that the solution is y is equal to 6 over x squared, right? Something like this. Okay, and that is the idea behind what it is that we are going to examine in this video. So this is the idea of solving exact ODEs. And so I need to write down the official definition. So we're going to write down definition. Okay. An ODE is what we call exact if it can be written in the form. So it can be written in the form where we have m of xy dx plus n of xy dy is equal to 0, and it turns out that m, our function m, is equal to the partial derivative of some parent function f dx, and n of xy is equal to the partial derivative of some parent function dy. If this is the case, if this is the case, then the left side of the equation, then the left-hand side of the ODE simplifies to be what I'm calling dz. And then the right-hand side, we still have we still have 0, so equals 0. And again, in case you're wondering where the z comes from, I'm using z and f interchangeably here. You could write df equals 0. You could have labeled all of these partials as dz dx and dz dy. Totally fine. But so if this is the case, then the left-hand side of this ODE simplifies to be dz equals 0, which has a very easy solution, whose solution is just, the parent function f of xy, or the parent function z, is equal to some constant c. Okay, that would be our solution. All right, so this is the theory. This is the whole bunch of, man, okay, cool, like that's nice if it happens, sort of thing. And the follow-up is, how do we know this is going to happen? So how do we actually check? How do we know? Or how do we try to check? How do we try to check that our m of xy is actually equal to the partial derivative of f with respect to x, and the n of xy function is actually equal to the partial derivative of f with respect to y? Like, how do we actually do this? And it turns out that the only criteria that we know that we need to prove is the following. So it turns out that as long as these functions are continuous, so as long as m and n are continuous, as long as m and n are continuous in the region we're trying to solve them, okay, and this just has to do with like existence and uniqueness, and we'll cover that a little bit more later. But it turns out that if these functions m and n are continuous, and dm dy is equal to dn dx, then the ODE is exact. Now, this might seem like a very weird thing to write down because I just got done defining what an exact differential equation is. The only thing is that in this exact definition, it requires us to know that m and n are these partials of f with respect to x and y respectively. But you don't necessarily know that that's the case. Like, if I just give you a random one that's like x squared y cubed dx plus e to the x dy is equal to 0, you don't know whether or not there is some parent function where the thing on the left is the partial derivative of it with respect to x, and the partial derivative of it with respect to y is e to the x. Like, you don't know that. It would be nice if that happened, because then solving this ODE would happen very quickly, but we don't know that that's going to happen. So we need this check, this very kind of strange check, and you can kind of very quickly see here that the example I wrote down on the right, it fails this check. Now, a better question is, why does this check work? If you've taken Calculus 4, you will know or have seen this proof before, but this is a result. Of Clairaut's theorem. Clairaut Clairaut's theorem, which basically says that if your functions are continuous, so if these partials are all continuous, if these partials are all continuous on our region, then it turns out that things like f of xy is equal to fyx, or basically that if you do the partial derivative with respect to x and then the partial derivative with respect to y, you get the same thing out as if you swap that. And so what this means is, right, if we suppose for a second that our function m, m is actually equal to the partial derivative of f with respect to x, and then we take the derivative of this thing with respect to y. So let's take the derivative of it with respect to y. We get this, but then by Clairaut's theorem, we're going to get that this is also equal to d squared f, but this is also equal to if we had swapped the order of integration. So now we're doing dy first instead of dx, and then I can split this into, well, let's use a different color, d dx times df dy, but this just ends up being equaling to the partial derivative with respect to x of our function n. And so basically it says that if these two do indeed come from this mystical magical parent function f of xy, then it needs to be the case that their second partials are that they're equivalent. We have like this bridge that kind of takes us from one to the other. So if we take the partial derivative with respect to y of our function m, we should equal the partial derivative of our n function with respect to x, and this guarantees that they came from some big bad parent function. And so I think it's time that we see an example of how this works. So for example, let's go back and let's consider the ODE that I wrote earlier. So consider the ODE that's given by dy dx is equal to negative 2xy squared plus 1 over 2x squared over 2x squared y. Okay, and that negative still is supposed to be inside or outside of that parentheses like that. Okay, so we have this differential equation. Some things to note is that this is definitely not linear, so we immediately cannot use the integrating factor method. And if you try to separate this into just the x's and just the y's, it doesn't work out. So it's not separable, which means we lose our two favorite methods that we know for dealing with first order differential equations. We lose separability, we lose linearity, and so the only other method that we hope will work is going to be this particular method. And as a hint, in this particular class, I'm not going to magically give you a differential equation that you can't solve using one of the methods. So if you realize, oh, not linear, not separable, you can kind of, there can be a little bit of an inkling that this thing is going to be an exact ODE. But we can try to put this in ODE or in exact form. So exact form, so we have 2x squared y dy is equal to the negative 2xy squared plus 1 dx. And then I can rearrange things one more time, and I'm going to get 2xy squared plus 1 dx plus my 2x squared y dy is equal to 0. Now, even though this is in like kind of what we say exact form, we still need to check that that these partials that I mentioned earlier, that the partials here are equal. Otherwise, this is then we can't use the solution technique that we just came up with. So we first identify that this thing right here is our m of xy function. We identify that this is our n of xy function. And the first thing that we're going to do is we're going to see if dm dy is equal to dn dx, this cross-pollination of partial derivatives. We want to see if they are equal. If they are, we keep going. If they're not, we give up, and this ODE is not solvable by the techniques that we have learned in this class. But thankfully, if we take this partial derivative, so dm dy, we treat y as our variable, x is its constant, so we're going to get 4xy out. And if we do dn dx, we are going to treat x as our variable, y as our constant, and we're still going to get 4xy out. And more importantly, both these functions are continuous everywhere, which means we don't have to worry about only being able to find solutions for certain values of x or certain values of y. So we have continuity, their second partials they're all equal, and so we keep going. We say check, this is exact. And so now we know that the solution, so we already know now that the solution is simply f of xy is equal to some constant c. But the thing that remains to be shown is, what is this parent function f of xy? Like, how do we do this? If we know it, then we are done with this entire problem. The nice thing is, again, if you've taken calculus 4 before, you will have seen this, and there are ways to do it, and you're going to learn it right now. And if you haven't taken calculus 4, you're going to learn how to do some kind of half integrals, if you will. And so here's the idea. The idea is that we need to recall that my function m is the partial derivative of f with respect to x, and my function n is also the partial derivative of f with respect to a different variable y. But in theory, if I were to take the integral of both of these, right? In theory, if I do the integral of my function m with respect to x, I should get my function f. And if I were to get the integral of my function n with respect to y, I should, in theory, end up back at the same function. Now, there's a caveat to that, but that is our guiding principle of how we are going to go about solving this. So, for instance, let's start with our m function. Let's take the integral of 2xy squared plus 1 with respect to x, because this is my m, this is my df dx. So we're going to undo that and hopefully get back to our parent function f. So if we do this, taking an antiderivative with respect to x, you do this the very same way you take kind of partial derivatives, which is we're going to treat x as our variable and y as a constant. We're going to add 1 to the exponent, divide by the new exponent, and we're going to get x squared y squared plus, so that takes care of the first one, plus x, that takes care of the second one, and normally there would be some plus c here, right? But the thing is that, remember, in order to check our answer, we would take the derivative, and it turns out that not only is the derivative of a constant equal to 0 when we're going back this way, but since we would be taking the partial with respect to x, we could have a whole function here in terms of y. This function could look something like y squared plus 3 or something like that, because not only will the constant evaporate when we take a partial derivative, but any function involving only the variable y would also evaporate when we take its derivative to check that we got back. So we say that the antiderivative here is x squared y squared plus x plus some mystery function g of y. But the important takeaway is that this is supposed to be our solution function f of xy. You say, okay, cool. But the problem right now is I don't know what this g of y is. So we're gonna hold on to that for a second. And now we're going to go below and we're going to do the same thing, but we're going to do it for our n function. Because if I take the antiderivative of our n, this 2x squared y, and I do it with respect to y, we should get back the same parent function. So again, we add 1 to the exponent, divide by the new exponent, and we get x squared y squared plus, and again, normally it would be a constant, but what's a constant with respect to y? We're going to get some function, maybe we'll call it h of x out. And this is supposed to also equal our solution function f of xy. Again, the problem is that here I don't know what h of x is, so we pause that for a second. And now at this point, we kind of like Frankenstein together what our solution function should be. So we look at this and say, look, both of these are supposed to be equal. And so you're like, all right, so my solution function f of xy, what does it equal? And you say, well, they both have an x squared y squared in common. So it definitely has that x squared y squared. Now, this function, this h of x, I don't know what it is, but I notice that over here I have some function of just x. And so if I had some plus x here, right? If this h of x function wasn't a mystery and it was actually x, then we would also have a match. And so we're going to pop in that x and say, oh, h of x has to be equal to that x function because both of these equations are supposed to be equal. And then similarly, we look at g of y and we say, hey, are there any functions of y? Is there anything left over here that we would need to, say that g of y is equal to? But there's nothing left over, so we come to that conclusion that this g of y, this plus g of y that we got, is actually just equal to 0. There's nothing else to add. And so I claim that this, what we just came up with, is our f of xy. It's this big parent function. And you can check, right? If I take the partial derivative of this with respect to x, hopefully we get back to here. And if I take the partial derivative with respect to y, we're going to get right back to here, which verifies that our m and our n were indeed these partial derivatives that we thought they were in the first place. And so what this means is that, our solution to this differential equation, remember, the whole point of doing this was that we know that the left-hand side just consolidated to be dz equals 0, and the solution to that is f of xy equals c, which means that our final solution to this differential equation is just going to be x squared y squared plus x is equal to some constant c. And this right here, solves the original differential equation that we were given. How would you verify that, right? You notice this differential equation, this solution is defined implicitly, right? It is implicitly defined. And how would you verify it? You verify that this is a solution the same way you verified anything, right? Remember that our ODE was this little thing up here. So all I need to do is to take my solution. I need to take the derivative of it with respect to y. I need to figure out what dy dx is. And I'm going to solve for dy dx, and I'm going to verify that it perfectly matches the differential equation that I got in the first place. So verifying something as a solution is the same thing you did that you did last week or in any of the homework so far, where you were trying to verify that a given solution was a solution to a differential equation. The process is the same. And so yeah, this is the process of solving exact differential equations. I do want to emphasize we are getting very lucky, right? If I change this differential equation just a bit and I put a cubed here and then I end up with a cubed over here, then our partial derivatives won't match, and this whole thing is now we need some other technique that we don't know about to try and solve this. So I do want to insert the caveat that just like in Calculus 2, when we would give you stuff and be like, you can solve sine of x over x, but as soon as I put like sine of x over x plus x squared, maybe it becomes harder. What happens if I put sine of x cubed over x or something, right? Like the idea is that as soon as we start modifying these integrals, they become maybe more difficult to solve, or to the point of even being absolutely impossible to solve, right? We can solve the integral of e to the x, but solving the integral of e to the x squared requires some really advanced techniques that you can't just do in a standard Calculus 2 class. So I do want to illustrate that these are very special types of differential equations. So hopefully that video was helpful, that you kind of understand what an exact differential equation is, the check that we need to do to verify if the differential equation is exact, and a little bit of the theory that kind of describes, where this idea came from Calculus 3, and hopefully it all kind of makes sense the more you do some practice examples. So I know there's only one practice example here, but it's a pretty well fleshed out example. And I think that if you tackle some of the homework problems, you're going to find that it's not too bad. If you're having any issues, definitely shoot me an email. This topic is a little funky, or post in the discussion. And I will catch you all in the next one.